Applications of determinants. The adjoint of a matrix. We learned in this chapter about cofactors, but just in case you missed that or need a little refresher, let's talk again very quickly about how to find a cofactor. If I want to find the cofactor of some entry, A11, that means the cofactor is found, so C11 would be -1 to the 1 plus 1, because it's first row, first column, and then Mij. Well, Mij means I'm taking the determinant of, if I were to take away the first row, first column, I'm going to find the determinant of A22, A23, A32, A33. And I could do that for any of the entries, and we have done that before, but that's basically how that works. So let's do one more to make sure we understand how to do it. A21 would give me C21, would give me -1 to the 2 plus 1. And then if I took away the row and the column, I would be left with A12, A13, A32, and A33. So again, and then I would find the determinant of that resulting matrix. That is a cofactor. Now, if I were to find the cofactor of every single element, I could make a matrix of cofactors. And if I take the transpose of that matrix, remember a transpose means that the rows becomes columns and the columns becomes rows. So this row becomes the first column, the second row becomes the second column, the third row becomes the third column. That is called the adjoint of A. Let's take a look at how to find an adjoint of matrix A. So here I have matrix A. I'm going to begin in the first position, row 1, column 1. Remember, I'm going to take -1 to the 1 plus 1. That's first row, first column. And then -2, 1, 0, -2 is what's left over. Just as a reminder, to find the determinant of a 2 by 2 matrix, we're taking the first diagonal, which is 4, minus the second diagonal, which is 0. So I'm taking -1 to the second, which is +1, times 4 minus 0, and that results in 4. And then I would continue for C12. So again, I would take out the first row, second column. That would leave me with -1 to the 1 plus 2, which is going to result in a negative value. So this is going to be -1. I'm left with 0, 1, 1, -2. When I cross multiply, I get 0 minus 1. So this is -1 times -1, and that gives me +1. And I continue that, and I don't want to take up a lot of your time doing easy math. But I'll go ahead and show each of these values, each of these cofactors. Now, if I wanted to put them all together, I could then make my cofactor matrix, which would be 412, 603, 712 in the same order in which I found them. But we're trying to find the adjoint, and so remember, to do that, I'm going to take the transpose of this matrix, and that's going to make rows columns and columns rows. So 4, 6, 7, 1, 0, 1, 2, 3, 2. Of course, then the question becomes why? Why do we care about the adjoint? So we just went through the work on how to find the adjoint, which I've written on this slide again. But we can use the adjoint of a matrix to find the inverse of a matrix. So if A is an n by n, so square invertible matrix, then A inverse, or the inverse of A, is 1 divided by the determinant of A times the adjoint. So if I want to find the determinant of A, you can do whichever row operations that you want. You can add, subtract, whatever. Any of the ways that we've talked about how to find the determinant. You can use the diagonal, you can use cofactor expansion, whatnot. The determinant of A is 3. And this tells me that if I take 1 divided by 3 times the adjoint of A, that's going to give me the inverse. And it's pretty easy math then, 1/3 times each of those values, and that gives me the inverse. Now, personally, this seems like a lot of work to find an inverse, but hey, it's just one more tool in our tool belt. Cramer's rule. Cramer's rule is an excellent way to solve a system of equations using determinants. So it's a great application of determinants. Now, I wrote the explanation that your textbook gave, but quite often with any mathematical definition or explanation, it can get a little hazy. So let me take you through an example and show you exactly what we're going to do. What we're going to do is we're going to think about our system of equations as a matrix. Remember, we always say AX equals B. So we're going to take A, which is the coefficient matrix, 4, -2, 3, -5. And then, of course, we would have x1, x2. That's not important for Cramer's rule. And then 10, 11. So that's AX equals B. What Cramer's rule tells us to do is to find A, the determinant of A, and the determinant of A1, and the determinant of A2. So the determinant of A is just the determinant of our original matrix, 4, -2, 3, -5. And that gives me 4 times -5 is -20, minus 3 times -2, so minus -6 or plus 6 gives me -14. Then I'm going to, because I'm dealing with x1, I'm going to replace the coefficients from x1. So this is determinant of A1, which means the first column, which is x1. I'm going to replace 4, 3 with 10, 11. So 10, 11, but still -2, -5. So then I'm just going to find that determinant. 10 times -5 is -50, minus 11 times -2 is -22, so that's plus 22, which gives me -28. And then I'm going to do the same thing. A2 would correspond to x2. So now I'm going to find the determinant of A2, which is the determinant of, we have 4, 3 still. That's the original 4, 3. But instead of -2, -5, we have 10, 11. So that gives me 44 minus 30, which is 14. Had to run out of room there a little bit. Now, the great thing about this is I haven't really broken a sweat mathematically. I didn't have to do a lot of work, but that gives me x1, the solution, is simply the determinant of A1 divided by the determinant of A. So that means this is simply -28 divided by -14, which is +2, and x2 is A2, or 14, divided by A, the determinant of A, which is -1. So I have solved this system just using a bunch of determinants. Let's take a look at using Cramer's rule on a 3-variable system. Now, before we get into using Cramer's rule, I do want to point out that we can still solve a system the same way we have been. So notice I have the system as an augmented matrix in E, and I can just row reduce E, and that tells me that the solution to this system, because notice on the left 3 columns, this is the identity matrix. That means my solution is 3, 2, 1. So that's what I know the solution is. But let's verify that using Cramer's rule. Now again, I'm not going to be showing all of the work for how to find the determinants. You can do it by hand. I just wanted to show you using Desmos as well. So I have A, B, C, and D as A1, A2, A3, and A. So to find the value of x1, which we just found out was 3, I should be able to find the determinant of A1, which in this case is A, and divide it by D, which is my A matrix. I know it gets a little crazy because I can't use subscripts in Desmos, but this is the original coefficient matrix: 1, -1, -1, 1, 2, -1, 2, 0, -1. So that's the coefficient matrix. A, notice I've replaced the first column with 0, 6, 5. So let's test the theory. I should get 3 as a solution, but this is telling me that I should take the determinant of A and divide it by the determinant of D. And notice I do in fact get 3. Let's do, and of course you can find each of those separately. Determinant of A is 9, which makes the determinant of D 3. So you can do it that way, or you can be lazy like I am. Now my next one should be 2, and that would be the determinant of B. And notice, again, B was replacing the central column with 0, 6, 5, the constants. And I do, in fact, get the same value of 2. And then I can do the same thing for x3, which is C. C was replacing the final column with 0, 6, 5. And then I find the answer is 1. So Cramer's rule and just row reducing give me the same solution of 3, 2, 1. Finding area or collinear points using determinants. We're going to begin by finding the area of a triangle. So we can use determinants to find the area of a triangle with corner points x1, y1, x2, y2, x3, y3. And we're going to use the formula, and it begins with plus or minus, and the plus or minus just says we know area has to be positive, so if you end up with a negative solution, make it positive. So now we're taking 1/2 times the determinant. The first column is my x's, the second column is my y's, the third column is all 1's. So let's take a look at how to find the area of this triangle. To find the area, I'm going to first write it in the correct format. So I'm taking the x's of 1, 0, -3, and put that in the first column, the y's of 1, 4, -5, and put that in the second column, and the third column is all 1's. You can choose which method you want to find the determinant. You can use diagonals, you can use cofactor expansion and whatnot. I believe below I've used diagonals, so that means I used 1, 2, -3, and 1, 4, -5. And then I said, let's find the product of the diagonals, so 4 and -3 and 0. And that is the way I did it, 4, -3, 0. I'm finding the sum of those. And then going in the other direction, we find -12, -3 times 4 times 1, -5 times 1 times 1, or -5, and 0. And I'm taking the first diagonal, the sum of the first diagonals, and subtracting the sum of the second diagonal, and then simplifying. So then I get plus or minus 1/2 times positive 18, and that gives me 9. So the area of this triangle is 9 units. For practice, I would like for you to find the area of the triangle with endpoints 0, 1, 4, 3, 8, 5 using the same method. When you are ready, press play to see how you did. Just as we did in our last example, we're going to start using the area formula, replacing x1, y1 with 0, 1, x2, y2 with 4, 3, x3, y3 with 8, 5. Now I'm going to go about finding the determinant. Again, I used the diagonal method, but you can use cofactor expansion or whatever method that you like best. But I went ahead and rewrote 0, 4, 8, 1, 3, 5, and then I started working. I said, let's take 0 times 0 plus 8 plus 20, which is 28, and that's the downward diagonals. The upward diagonal is 24 plus 0 plus 4. And in this case, if you'll notice, I get 28 minus 28, which is 0. So you might be thinking, uh-oh, I made a mistake in my work. And that's not the case. If I were to graph this, if you'll notice, these are collinear. So we actually have another way to check if there are points that are collinear if you end up using the same method that you used for area, but if you get a determinant of 0, the points are collinear. Finding volume using determinants. You can also use this method to find the volume of a tetrahedron. Now, I don't have a picture of the tetrahedron. It's essentially a triangular prism. So it's a triangular base with a triangle for each of the three faces. You can find a great picture in your textbook in section 3.4, of course. And in fact, I used the same endpoints or vertices as your textbook used so that you could look at that exact picture and see what's going on. But essentially what we're going to do is try to find the volume. And to find the volume, you're going to use the same method, but with the last column being ones, but obviously there are going to be 4 rows for the 4 different points that you're using. So using these 4 points, notice I've already set up matrix A. What we're going to do is find 1/6 of the determinant of that. So I'm going to take 1/6 and I'm going to multiply by the determinant of A because I didn't feel like doing all of the work myself. And so I could say that the volume of this tetrahedron is 12 cubic units. Now, I could obviously have done this work by hand. This one in particular lends itself well to cofactor expansion using that second row, but I took the easy way out on this one since I just wanted you to understand the concept that you're taking 1/6 times the determinant. Equations of lines or planes using determinants. We can use the determinant of a matrix to find the equation of a line passing through 2 points. So in that case, we're going to keep the first row as x, y, and 1. And you'll find that in doing so, we're able to do cofactor expansion using that first row. Now, before we use that, I just want to point out that a lot of times in mathematics, there's more than one way to find a solution. So before you were in linear algebra, if I asked you to find the equation of the point passing through these 2 points, the equation of the line passing through these 2 points, you would probably start by finding the slope and say that second y minus first y divided by second x minus first x. And that would give me -1 over -3 or 1/3. And then we would use point slope form, so y minus the y value of 4 is equal to the positive 1/3 slope, x minus the x value of -2, so that's +2. I would go ahead and distribute the 1/3, so that gives me 1/3 x plus 2. Plus 2/3. And then I would add 4 to each side, so that would give me y is equal to 1/3 x, and then adding 4 to each side would be the same as 12/3. 12/3 is equivalent to 4, so that would give me 14/3. Now, when we use this determinant method, what we're going to get is not the slope-intercept form, but the point slope form. So let's just take everything times 3, just so we can compare. I would get 3y is equal to 1x plus 14, and then I would rewrite that as x minus 3y is equal to -14 by subtracting 3y from each side and subtracting 14 from each side. So that's what I get. Let's now take a look at doing this using determinants. So what I would do is I would write my matrix. I would replace x1, y1 with 1, 5, x2, y2 with -2, 4. And from here, I'm just going to do cofactor expansion, and I'm going to use always the first row. And the reason for that is if I'm using that first row, then I'm getting x. So this, keep in mind, this is -1 to the 1 plus 1, which is positive. That's why that one's positive. And then 5, 1, 4, 1. And then the next one is -1 to the 1 plus 2, which is why I end up with a negative here. So feel free to show the negative ones if you want to, but it's always going to be plus, minus, plus. And again, I'm left with 1, 1, -2, 1. And then the last one would be plus again, and then 1, 5, -2, 4. And then, very important, is equal to 0. From here, I'm now just going to use the determinant of a 2 by 2 matrix, which says I'm going to take 5 times 1 and 4 times 1. So that gives me 5 minus 4 times x. And then 1 minus -2, or 1 plus 2, notice I'm still keeping that negative out here, times y, and then I didn't put the 1 here, but you sure can. 1 times 4 minus negative 2 times 5 gives me plus 10. And then I'm going to simplify. 5 minus 4 is x minus 3y, and then this gives me plus 14 is equal to 0, so I kind of skipped a step in there. And then I subtracted 14 from each side. And I want you to notice that gives me the same result I got doing it by hand using algebra. We can repeat a similar process to find the equation of a plane. An equation of a plane is going to give us 3 points, and we're going to use the same strategy. The first row will be x, y, z because we now have 3 points in 3 dimensions. The final column will be all ones, and the remaining part of the matrix will be the 3 ordered triples. Now, as you can see, we're going to find the equation of the plane passing through these points. And the thing that you want to keep in mind when using Desmos is that you still have to be smart enough to know exactly how this is going to work out. So when we just did this using using the equation of a line, we said the first one would be positive, the next one would be negative, the third one would be positive, and so on. We're going to do that same thing again. So I have all of the cofactors here, and I'm going to go ahead and find the determinant of A, which is 4. I'm going to find negative determinant of B because that's the second one, so that would be first row, second column, or negative 1 to the third. I'm going to find the determinant of C, but I'm going to find the negative determinant of D. So what I have here is essentially 4x minus 3y plus 5z plus 3 is equal to 0. And of course, I'm not going to leave it like that. I want the 3 on the opposite side, so I'm going to subtract 3 from each side to give me the equation of the plane. 4x minus 3y plus 5z is equal to negative 3. We can do the exact same question that we just did using another strategy. So as you can see, this is the same determinant, or the same system of equations that I had previously, the same setup. If I didn't want to use Desmos to find all of the 3x3 determinants, I can also do a little bit of math. So I can subtract the fourth column from the second column, and as you can see, that gives me y minus 1, 0, 2, and negative 1. And then I can use cofactor expansion along this row to essentially end up with, this 3x3. So that's what I'm going to be working with. And it is going to be positive because I ended up with the second row, fourth column, so that's negative 1 to the sixth. So I'm finding the determinant of this new, smaller matrix. Now, why is that helpful? Because I can do the math quite easily now. I can do cofactor expansion along the first row as I did before. So that would give me x times the determinant of 2, 2, negative 1, 1, and then minus, because remember that's the second one, so it's minus, and then I have the quantity of y minus 1 times negative 1, 2, negative 2, 1, and then I have z times negative 1, 2, negative 2, 1. For my next step, I went ahead and distributed this negative. So notice on my second row of work, I'm calling that 1 minus y. So it's a positive 1 and a negative y. And that's just so I don't screw up the signs, because it's easy to screw up the signs when you have minuses and negatives and all of that. But then I just found the determinants. 2 times 1 minus 1 times negative 1 times 2. And then negative 1 times 1 minus negative 2 times 2, and negative 1 times negative 1 minus negative 2 times 2. And then I simplified each step, so that gives me 4x, and then this is 3, so it's 3 times 1, or 3, minus 3y, and then plus 5z, and then as I always do, I just moved that other value to the other side, and if you'll notice, we got the exact same equation for the plane that we did using Desmos. Coming up next, we're moving on to chapter 4, and we're going To talk about vector spaces.